Okay. I want to, first of all, take a look at the syllabus. I just wanted to point out to you that the data sets, the .text files that you need to import for the notes are where it says data files or book data sets. So if you click on that, it will download a folder. It's zipped, should unzip. And I'll keep adding to that as I run across data files that you're going to need for the lecture. So I just wanted to point that out. And then next, I have posted this morning, in fact, so if you downloaded yesterday, they're updated. I've posted a slightly revised version of Chapter 9 plus the Chapter 10 notes. So I want to finish Chapter 9 today and then get into 10. We need to move a little bit more quickly. So let's go into our studio. So I'm going to start with Chapter 9. So what happened to the .rnd file accidentally? This is something that's occasionally a problem. I try to be very careful about this, but I hope I didn't mess up the wrong file. So what I'm going to do is go in and mount the server. And actually I'm going to go back into the notes and download. I certainly hope this is the latest version. Too many things open. You have to be careful when you're dragging files that you hold the Option key down. Otherwise it moves instead of copies. It's probably what I did by accident. We'll get there. So now it should be here. Right. Yes. By the way, that's something you can do. So I'm going to set the working directory. I don't know what extent that I'll need to look at the workspace, but Let's go ahead and knit this so we can look at the output. I'm just going to quickly tell you what we did last time. So last time we talked about linear regression. We talked about the model y is equal to alpha plus beta x plus epsilon. Epsilon, later on you'll see we're going to assume that it's independently normal if mean is 0 and variance sigma squared. We have to estimate, there are two parameters in the regression model, alpha and beta. So we need to estimate both of those, and we'll use the method of least squares. We actually also will need to estimate sigma squared when we make inferences about the parameters. But for now, I had talked last time that if you want to minimize the sum of squares of deviations, that is, if we fit a line, we want to deviate these vertical lines. We want to draw the line such as sum of squares of those vertical lines, that is, the difference between the y's and the y hats, are minimized. And to do that, we have a quadratic. We take derivatives with respect to a and b and set them to 0. And since they're quadratics, they become linear. So we have a system of linear equations, in this case of 2 equations and 2 unknowns. More generally, we'll have more x's in our model. And so we get a larger system of linear equations in that case. So we'll be doing that, I believe, in chapter 14, when we look at multiple regression. But for now, we have a system of normal equations that are fairly easy to solve, and we can get beta. It's the sum of the corrected cross products of the xy's with the divided by the sum of the corrected x sums of squares. And so that gives us b. And there are 2 ways to compute them. The second method is what you would use with the calculator. The first method is what you can use here. Although R doesn't use either one, it uses a much more efficient system called the QRB composition. We can get the intercept A as y bar minus bx bar, and again, that derives directly from the normal equations. Then I had an example where we had miles before hitting the wall. No, I'm sorry, this one is, sorry, that was previously. We have blood pressure, systolic blood pressure, and we're trying to see if there's a relationship between age and systolic blood pressure. So we read in that file, and again, in this case, it was a little data set, we created a data frame directly. And then we attach it so it's on the search path so we can use the names directly. And so we fit a model LM. LM stands for linear model. In this case, it's a very simple model. Systolic blood pressure tilde age, and that just means that systolic blood pressure is modeled, modeled as a function of age, in this case a linear function. And so systolic blood pressure, again, it goes by dependent variable, outcome variable with various names. Age is the predictive variable, explanatory variable, independent variable. Those all mean the same things. And a lot of times we'll look at the scatter plot, and in this case we can look at the scatter plot, but we can also superimpose the fitted line. And this fitted line, I saved it as an R object called fitBP, and you can actually extract the straight line directly from that object. So I say AB line, after I say plot, age by systolic blood pressure, I say AB line fitBP, and that actually extracts the slope and the intercept and plots it. So what does fitBP look like? If I print the object, R will have some print representation, and for this initial print representation, which is the default print for the object, it just gives you the model, plus it gives you the parameter estimates, and that's it. Then what I showed you is how to compute these S sub x's and S sub xy's by hand in 2 different ways. And so we computed B and A by hand, and you can see that they agree with using the LM function. So that was more just a case of showing you this is the way you would do it by hand, and you get the exact same result. Then we talked about model testing, and you can test for hypotheses about alpha, that is the intercept, but usually not. Sometimes you hypothesize that the intercept is 0, that is, that the line goes through 0. That's not very common. And so I'm not going to focus on testing hypotheses about alpha, but what is important is testing hypotheses about beta. And in particular, you want to know, is the regression line significant? And so if, in fact, beta equals 0, it means that it's a horizontal line, and we have no predictive capability using our model. So we want to test that beta equals 0 versus unequal to 0. Now, of course, in general, you might do a one-sided or a two-sided test. Usually in these types of models, it's one-sided, however. So you can have a general hypothesis that beta equals beta naught, where beta naught is specified. By default in R, you're going to test it at 0, and you'll see later on when we have a summary. We can do this with a t-test, and it's simply the estimate beta and the estimate of beta, which is b, minus the hypothesized value, which is often 0, over this estimated standard error of b. And it turns out that the estimated standard error of b is simply sigma hat, which is like an estimate of that variability around the regression line, divided by the square root of the s sub xx, which is the sum of it's the corrected sum of squares. So that gives us a t-test. Now, how do you get the estimate sigma hat or sigma hat squared? Well, we're going to call it s squared sub y dot x. The y dot x means y modeling x. So we want this is the residual variation of what our model doesn't fit. So it's a sum of the y minus the y hats, the sum of the y minus the predicate values squared. And just like when you did y minus y bar squared, where you were estimating one parameter, y bar estimates mu, you divide it by n minus 1. When we get y hat, we're estimating two parameters, alpha and beta, and so instead of having n minus 1, it's n minus 2. And this gives us an unbiased estimate. Now, what I showed to the right of that is simply some computing formulas that you can use. If you've already computed s sub y and s sub xy, then you can easily, and you already have b, or if you don't, then this the third form you can use. At any rate, those last two are more appropriate when you're doing things by hand. As you'll see or have seen, R does all this for you, and so you don't actually have to do these hand calculations. So the estimated standard error then is s sub y dot x divided by the square root of s sub xx. So this quantity right here is what we need in the denominator. And the numerator is typically just b, unless beta naught is not 0, but as I said, it almost always is. Now, it turns out, we can certainly do those by hand, but if you say summary of the object, so if I say summary of fit pp, so fit pp is the model object that I created using the LM function. If I say summary of it, it gives lots of stuff. It gives the formula, but it gives a lot more than just the coefficients. The default print method for the object itself only gave the model and the coefficients. But if you say summary, you get much more. And you get a little bit on the residuals, the min, the max, and the quartiles, as well as the median. And then you get the coefficients, but you also get the standard errors of the estimates of both of them. And then if I take the estimate divided by the error, standard error, I get the next column, which is t. So if you take this first column and divide by the second, you get these t values over here. And you'll notice that both are highly significant, which means the regression equation does have significant predictability. Now, the test for the intercept is not that meaningful because you're testing alpha equals 0. And, well, unless you really think the data goes down through 0, it's not a very meaningful test. But the beta equals 0 is, and this says that we should be able to predict using this model. So there is there is an upward trend, but you notice there is a lot of variation, but nonetheless it is highly significant. In other words, systolic blood pressure tends to go up with age. And we know roughly that it's going up about 0.62 for every increase in 1 year. That's the slope. So at any rate, so we had computed A and B before, and the systolic blood pressure hat, I have three values here. I have the hat, which is the y, that's the y hats, which is this A plus B times age. We've computed A and B, so we can compute this quantity. Then the residual is this y minus y hat. And then this is actually the computation of the S sub y dot x, and that's the square root. In this case, I computed it as the square root of the sum of the y minus y hats squared divided by n minus 2. And so that's 4.28. And you can verify all of these quantities. So that 4.28 in the output, is computed by hand right here. And then here's the t-value, which corresponds to this t-value up here. And here's the p-value, which takes the computed t, and we need the upper tail value, and then we double it because it's two-sided. And that p-value is 0.0038, and again, it's right here. So what I did below is I replicated some of the numbers in a table above just to make sure that you see how to do it. The model assessment, we want to assess normality, which we can do with a histogram, although that's not very good. So typically, the second one, we construct normal probability plot. And in linearity, we can plot the errors, that is, the residuals versus the y-hats, to see if they're randomly distributed about the regression line. Equality of variance, we can plot, typically we would plot the residuals versus, in this case, age. And independence is something we sort of know from the context of the problem, whether or not we have independence. So that is, again, the histogram might be better if, in fact, you had a larger sample size, but assessing normality from this is not so hot. It does appear that we have reasonable normality, although there's a bit of curvature. You can see there's a little bit of curvature on each end, and so you can see that it's the residuals are a little bit skewed to the right, which you can sort of see from the plot. And then this is the this is testing. This is sort of linearity, and again, that's fairly good, except for maybe this one outlier. And then equality of variance, which again looks pretty good, except for that one outlier. Okay. Now that's more or less what we did last time, so that's why I went so fast. So now I want to look at the prediction problem. Suppose you want to predict the mean at a given x. And you might, and so that if you want to predict the mean at a given x, that means if at a given x you sampled a whole bunch of patients and measured the systolic blood pressure, what do you think the average value would be? And you put some confidence interval on that. You might also get the prediction of an individual value. So if you think of it, for example, as college admissions, and you're looking at high school GPA, and does high school GPA predict college GPA with some measure of success in college? So what an admissions officer has to look at is things like the SAT, your high school GPA. But let's just suppose they had the high school GPA, and they actually might ask two questions. If someone has an ACT, let's suppose it's, well, let's say it's a 3.2 GPA. Then what would, for that group that have a 3.2, what GPA do you think they'd have in college after, let's say, 2 years? And then you might say, for everyone in that group, what do you think the mean would be? And so that's actually predicting the mean, which we call mu well, I call it right here, mu star sub x, which is the expected value y given x equals x star. And so if we want a confidence interval on that, again, it's going to be the predicted value at that value of x plus or minus the t times that s of y dot x. And then we have something that's a little bit complex, the square root of 1 over n. And so we're predicting a mean, so you might think that if you're looking at the variance of a mean, then the variance of y bar will be s over the square root of n. So if you look at the first part of this equation, this is sort of like the s right here, and there's the square root of n. But it turns out that it depends on where x is. As x gets further away from the mean of x, in fact, this standard error, which is what this is, it's standard error prediction, which is this piece. Everything to the right of that t-value is the standard error prediction of the mean. It also depends on where x is. Now, and so that's x star minus x bar. That should be squared, I think. I'm pretty sure that's squared, yeah. And so if you look at that divided by s of xx, that's sort of the additional variation you have, because when we get away from the mean, we have less predictability. And I'll show you what this looks like. The mean is actually, I compute it someplace. Yeah, the mean right here is 34.6. So if you look at this graph, the mean is right about here, 34.6. So it's right up through here. Do you notice that, and this is the predicted value at the mean, so right on that black line in the middle, that's y hat at the mean of 34.6. Now there's a group, you see that the group of inner lines and then the group of outer lines. The group of inner lines is going to be the confidence band. Do you notice that the band gets wider as you get away from the mean? Well, that is because of this piece right over here. In other words, x star, which is what the value I want to predict at, which I'm going to actually initially do the mean. But if you want to predict at x star, so it's x star minus x, that should be squared, divided by s of xx. And so as x star gets away from x, the mean of x, the band gets wider. And it gets wider quadratically. So that's why the bands sort of go out. And I'm sorry, it's this one actually. Now, in addition to that, we have a slight variation on this formula for the standard error if, in fact, we're predicting just an individual value. You see, that first one was predicting a mean value, the mean at a given x, the mean of y at a given x, whereas the next thing we want to predict is a predicted value. So let's suppose that a college admissions officer says, okay, what about Joe? One specific person. I want to know whether Joe is going to make it. Now that's not the same as saying that all students who get a certain GPA in high school, are they, what's their, how likely are they, where are they likely to fall? I'm saying, where's Joe going to fall? Well, because it's just Joe, there's more variability. And so that's where that one gets entered in when you have a single individual. And we have basically the same confidence interval, except the difference between those two equations is, in fact, the one. There's more variation when I'm trying to predict a single individual than when I'm trying to predict the mean. It's sort of like this. If I sample a single observation, it has a variance of sigma squared. So I pull out one observation, and let's suppose the variance of the population I'm sampling from is sigma squared, so it has a variance of sigma squared. But if I pull out 10 and get y bar, what's the variance of y bar? Well, it's sigma squared over 10. Or to put it another way, the standard error will be the square root of that. It will be sigma over the square root of 10. So it's sort of the same thing here. I have more variation when I have a single individual I'm trying to predict. It's much harder to predict a single individual than it is, say, the mean of a group of individuals. And so this is what we have. And so it turns out, here's the process of doing this. If you did this by hand, and particularly if you wanted to get a band for all values of x, and you wanted to do that by hand, you'd be spending a little bit of time doing it by hand. Fortunately, it's pretty easy to do in R. So, so first of all, I'm going to go through a few of these, but just let me sort of show you the idea of what we're doing. The mean of age is 34.6, and is a function called predict. And what predict will do, it will take the model object, and then it takes a data frame with what you want to predict. And so this is kind of overkill here, but I have to actually, I'm going to create new, something I want to predict, and it has to be a data frame, and so I'm going to say age equals the mean of age. In other words, I'm going to create age as the mean of age as my single value. I'm going to predict that, and then it says interval equals confidence. And what this does is gives the confidence interval, and that's the fitted value at the mean of age. Now, if I want the 95% prediction interval, that is for a single individual, then I do exactly the same thing, except instead of saying interval is confidence, I say interval is prediction. Now, notice these two intervals right here. Here and here. Which is wider? The prediction interval or the confidence interval? Well, the prediction interval goes from 64 to 85, whereas the other one goes from about 72 to 78. The prediction interval is quite a bit wider. And if you want to see that graphically, at the mean, which is about here, you can see these inner two curves are the confidence interval, and right in, I should draw a vertical line at the mean here. And then this outer, you see how big the outer ones are? Those are the prediction intervals. They're quite a bit wider. Now suppose I want to draw those curves. How do I do that? Well, to draw the curves, I'm going to create a bigger data frame. I say new gets data frame age equals sequence from 23. Now notice that the graph goes from, I want to go from about, I want to go from over the range of the x's from about 23 to 52. So I'm going to create a sequence from 23 to 52 by increments of 1. So age has what values? 23, 24, 25, 26. It's a quick way of generating a sequence of ages from 23 to 52. And then that's my new, and now I do the same, predict function with confidence and predict, and I get C limits and P limits for confidence limits and prediction limits. I'll show you how that goes in just a second. And so here we have, and then I have what's called a matrix plot, MAT plot, which actually will take the new age, it will take the new age as the x-axis, and then it takes the C-bind, or the C limits and the P limits, and I'll show you why you need that -1, because each of those gets the predicted values, and I don't want them twice, so I'm going to remove the first one. And then the line types just differentiate how I draw the lines. Type equals L means I want a line as opposed to points. And then I have a X lab and Y lab for the labels of the axes. And then we get this particular figure. So what I'd like to sort of do is step through this, and I need a few things earlier on. So I need to read in BP. Okay. And I'm going to attach BP, so I need to do a few things here. I'm going to attach it. I'm going to get the fitted value for the model. Okay, now that I have that, I don't think there's anything I need until I get down to, I'm going to skip over the testing. I think we've already gone through that. I want to get I want to go down and look at the code here. So first of all, I'm going to get the new value. So if I type out new, it's a data frame. Ooh, well, I actually meant to type out new over here. Okay, so that's actually a data frame, and now I can get my prediction limits here, and so that's how I get for the mean. That gives me the confidence limits at the mean. That is, at the mean age. And then if I want to get the prediction limits, let's see, yeah. If I want to get the prediction limits, those are the same values I had before. Now what I want to show is that if I get the C limits, now what this is, if I want, I'm going to create a data frame for age equals sequence 23 to 50 by 1. Let's take a look at what that value in new is. So new is a data frame that just has the values going from 23 to 52. Is that clear? Okay. Now I'm going to get the confidence limits. I'm going to have interval equals confidence. And so here are my, let's take a look at, and let's see what those C limits are. I'm going to just look at the first 5. So here are the first 5. So what it has, and this will be ranging from, the first one would be the predicted value for 23, 24, 25, 26, 27, and so forth. So those are the first 5. Those are the fitted values and the lower limit and the upper limit. They're actually, that would keep going all the way, to 52, right? Until age equals 52. So those are those limits, and then I'm going to compute the prediction limits. And let's look at the P limits. So if I look at this, and oh, that's actually not what I want to do. I just want to print, I want the, let's print out the first 5 again. Okay. So you can see these are quite a bit wider than the prediction limits are quite a bit wider than the confidence limits. But actually, I'm only printing out the first 5. Again, it goes from 23 to 52 by increments of 1. So I only printed out the first 5. Now what I'd like to do is plot a graph that has the predicted values as well as the 2 sets of limits. So I've got the bands, I've got the upper and lower band, I've got the upper and lower limits for the confidence interval, and I got the upper and lower for the prediction interval. Now you notice that when I do this, I can do a matrix plot. If I do a matrix plot and run this, that's the same plot I did before. So going from 23 to 52, I'm plotting the predicted values in the middle, and then the 2 inner lines are the confidence limits, and the 2 outer lines are the prediction limits. Now, if you look at my code, I said the x value will be the new $sign age. It will be the new age. It'll be the new age values from 23 to representing 23 to 52, and then I C bind. That means column bind. The C means column, and bind means bind together the columns. So I'm binding these 3 columns with these 3. So you actually end up with 6 columns. But there's one problem. The fit appears twice, right? So I bind the first set with the second set, so it becomes 6 columns,
And then the values go, again, from age equals 23 down to age equals 52. But I would be plotting fit twice. So the -1 says, so I have this group and then the second group here. And in other words, this second group gets bound on the right-hand side, you can think of it. So that -1 simply means eliminate the first fit. So it's eliminate. You've got fit twice. So the -1 means remove that first one. So when I do that, I have the lower and upper limits and lower and upper limits. I don't care if they're the same. They're actually not the same. They have the same values in terms of labels, but in fact they're different. So the matrix plot allows us to plot that, and the C1123, the 1, 2, 2, 3, 3. Actually, I think that if I change this, I might get a better plot. Let me see what happens. Since I subtracted -1, suppose I do this. Let me just try this and see if the graph works a little bit better. The color is still not coordinated. I was trying to get the outer two the same color and the inner two the same color, and apparently that's not happening. There's probably a way to do that, but the line types are correct. I guess what I'm going to have to do is specify some sort of color option, because what I'd really like is these outer limits, the prediction limits, to be the same color, and the inner limits to be the same color. So I think what I'm going to have to do is use some color option to get that. At any rate, that's how we get it. Are there any questions on this? So if you're trying to predict if you're trying to predict the mean, you get a fairly accurate prediction. But if I'm trying to predict an individual person, I don't. And that's mainly because, presumably, that you have a very small sample size here. If we had a larger sample size, we'd probably do a lot better. Okay, any questions? Okay, let's go back and look at the final topic in this chapter, and that's correlation. This is called the Pearson correlation. The correlation is a measure of how strongly in this case, age and systolic blood pressure are related. We know that there's a very significant regression. That is, we can predict systolic blood pressure with age with some level of confidence. But what I'd like is a measure that I could use, and I can't use B. Can anyone tell me why I can't use B? We know it's positive, but in this case it is positive because as age increases, systolic blood pressure. So we know it's positive, but why is it not a good measure? Well, it depends on the units of measurement. In other words, B has units of measurements the units of y over the units of x. So y would be what, in millimeters of mercury? And x would be in years. So if I changed age to, instead of how many years old you are, how many months old you are, then B would become quite different, because the inference wouldn't be different. That is to say, changing the scale won't change the t-value, but it does change B. We say that the t-test is invariant with respect, to the scale change. It doesn't depend on the scale, but B does. And so I'd like to get something that would be independent of the scales of measurements of y and x. So what I could do is divide by something if I take B and multiply it by something in the numerator that cancels out the x, and something in the denominator that cancels out the y, then I get a unitless measure. That is a measure that doesn't depend on units of measurement. And so one of the things I could do is take the square root of the s of xx, which is the corrected sum of squares of the x's, take the square root of it. That will have the units of measurements of x. And if I take the corrected sum of squares with respect to y, the square root of that has units of y, and so that gets rid of our units. Now, it turns out that if you do that, it's s sub xy then, if you look at the definition of b, which is s sub xy divided by s sub xx, then you get s sub xy over the square root of s sub xx times the s sub yy. And we can think of that as the covariance. Another way to think of it, if you divide all of those, if you standardize those by the sample sizes, then, or in fact, the sample size is -1, then you would find out you actually, in the numerator, have what's called a covariance, and in the denominator, you have a square root of a product of variances. And that's the normal definition that's given for the Pearson product moment correlation, R. Now, R has the property that it's between -1 and +1. A 0 means no correlation, and a +1 means a perfect positive correlation. A -1 means a perfect negative correlation. I don't know if this is still working or whether things fell asleep here. Let's see if I can bring it back to life. Problem is, when it falls asleep, everything goes. There we go. So, if we have data, and this is x and this is y, if the data is sort of circular like this, the correlation is going to be very near 0. R will be very near 0. On the other hand, if there's a fairly strong relationship going this way, it will be a very strong positive correlation. So this would be the case that the correlation, which this is the estimated correlation, would be fairly big in a positive direction. And if, of course, it is going down, then it will be a negative correlation. Now, you probably know that, but you can get into trouble. And as R approaches 1, the data is sort of approaching the point where it falls on a straight line in a positive direction. And it's -1 if it's approaching a straight line. That is, if all the points if they fall on or near a straight line that's going up and to the right, then it's a very high positive correlation. If in other words, you can think of it as kind of ellipsoidal, and as the ellipsoidal gets sort of fatter and fatter, then the correlation is going towards 0, and ultimately, in sort of a circular way, the correlation is going again to 0. And here we have sort of this ellipse in the negative direction. So depending on the width of that ellipse, it's some measure of correlation. But I did want to show you one thing you have to be a little careful of, and that is that you could have a very strong relationship between x and y. So you could have something like this, and if the data fell in there, it turns out that you would compute the correlation would almost be 0, even though there's a relationship between x and y. But in this case, it's a quadratic relationship. And if you look at how the correlation is computed, and if you sort of make a quadrant, then it turns out that you get a plus contribution here to the correlation, in that direction, and here you have a plus minus, and here you have a plus minus in the opposite direction, here and a minus minus. Whoops. So these two are contributing plus, and these are contributing minuses. In other words, here and here are contributing minuses, here and here are contributing pluses. So this is contributing plus to the correlation. So if the pluses sort of counterbalance, if they're counterbalanced by the minuses, R will be near 0. So even though that has a curvilinear relationship. So what R picks up is the linear relationship. If there's a nonlinear relationship, you can have a fairly nonlinear relationship and still have R near 0, is my point. So it's always important to plot the data to sort of see, what's going on. Because you could actually, if you just sort of blindly did a regression, you would actually have, your estimate of beta would be near 0 in this case. And yet we clearly have some predictive capability if we know X. Now, that's rather extreme. A lot of times what you may have is some sort of something like this, where if you look at X and Y, as X increases, Y increases, but it starts leveling off. Maybe it even becomes asymptotic to something. So the relationship is going very fast, but then it starts leveling off as X gets big. And again, that's a nonlinear relationship. Although in this particular case, you may capture it by a quadratic equation. In other words, not only have X in the model, but you have X squared. So sometimes you have a simple model that you can just put another term in what's called polynomial regression. But we're going to be looking at it later on in the course. So just be aware that you need to pull out the data and look, and if it's very nonlinear, then doing a linear model is you're going to approximate this with some sort of straight line, and you're going to have negative and positive residuals. But you can notice, I drew the line a little too far down, but you can notice that if you get y minus y hats, so a y here is going to be positive, whereas a y here is going to be negative residuals. So that's why it's important to look at these residual plots. If you see a pattern, if you're going from negative to positive to negative, when I plot these residuals, that indicates a pattern. And so that was why, that's why we were looking at these graphs here, for example, linearity, where we were looking at the y hat, and then the equality of variance, where we were looking at the with age. Now, another thing that could happen is if you plot, it turns out that if you look at the residuals, and in this particular case, let's see, which one has age on it? Yeah, this one. If you look at the residuals versus age, let's say, suppose they would have, and here's 0, and suppose the residuals would go like that. So the residuals would go, sorry, got to remember to switch back and forth. Yeah. So if the residuals are increasing, so these are the residuals plotted against age, this indicates that the residuals are increasing as age gets greater. So in that case, even though you may have a linear model, the residuals are getting bigger, and that indicates inequality of variance. And that was one of the assumptions. The residuals should stay the same. So what you want is the band to be about the same on each side. The residuals should be plus and minus, about the same amount on each side. But if the residuals form this, this sort of vortex or this funnel-type phenomena, then that's an indication in this case that the residuals would be increasing, and that means you violate the assumption that the variances don't depend on X. In this case, saying the residuals don't depend on age. Now, we didn't get that. That didn't happen to us, but I'm just saying it could happen to you. And if that does happen to you, then you might be looking at some models. Can anyone think of a model where this could happen? Now, the mean linearly depends on age in our case. But suppose the variance also increased as age increased. Suppose the variance increased with age. Then what type of model do you think you might have? Well, there's one distribution in which the variance equals the mean, and that's the Poisson. So what happens with the Poisson is as the mean goes up, the variance goes up. So a lot of times, if you're doing if you're, say, a biologist, a wildlife biologist perhaps, and you're doing counts, a lot of times those counts are distributed as a Poisson. So what happens is if I'm trying to measure these counts, and I'm doing something with them, and I'm trying to predict the counts based on something else, if the counts are really distributed as a Poisson, then it may not be surprising, that you have a relationship between the mean count and some predictive variable. That very much could happen. And so, and in that case, if we really have a Poisson, what we call a Poisson regression model, that is the y's are Poisson distributed instead of normally distributed, then we actually need to we need to do one of two things if it's a serious problem. We need to either transform the data to try to get rid of it, and sometimes we'll take logs of the square roots of the counts, and maybe that will help. And we'll get into this later in the course. But the other thing we could do is simply do a Poisson regression. Now, the Poisson regression goes a little bit beyond what we're doing in this course. That's taught in our Stat 555 course. So at any rate, I've got to set this thing so it doesn't go to sleep. So those are just a few points to think about. The diagnostics, in our particular case, the diagnostics weren't too bad. When we look at them, they weren't too bad, but don't assume from that that's always going to be the case. So in this case, if the variances would have sort of been funneling up, that would indicate that the variance depend on the mean, and that's a violation of an assumption, because we're saying that if you look at the model, you were saying the mean depended on x, or age in our case, but we said that the variance didn't. The variance was constant, didn't depend on age. So the residuals should therefore be in a band about 0, some positive, some negative, but there shouldn't be a pattern. So just to sort of summarize, we can keep going back and forth, a couple things you don't want to see when you plot the residuals. So if we're plotting the residuals, and let's say this is 0, okay, we don't want to see a residual pattern like this. That would indicate a quadratic term needs to be added. So, in that case, we don't want to see that. We also, if we're looking at the residuals, we don't want to see residuals looking like that, which indicate that the residuals are increasing with, say, x. So, and in this case, this gives us a lot of diagnostic information. Now, even in the case of multiple regression, where we have more than one x, we can do similar type plots, so a little bit more sophisticated. But we have ways of doing nice graphs, so we can kind of look at each x to try to get a feeling for where we're violating the assumptions. Okay, getting back to correlation, we can test. R is the sample correlation. Rho is the population correlation. You can think of it as what R approaches if the sample size goes to infinity. So rho is the population. Rho is the population product member correlation, and R is the sample product member correlation. It turns out that we can test rho equals 0 by a t-test, which is R, which is sample correlation, divided by the square root of 1 minus r squared over n minus 2. And so I actually compute this t-test. So S sub y, I need, right now I've computed S sub xy and S sub xx, but I haven't computed S sub yy. So if I compute S sub yy, then I can easily compute R to be b times the square root of S sub xx divided by the square root of S sub xy. And if I do that, I get a correlation of 0.8168. Now I could, of course, R has a built-in function called core, C-O-R, so I can just say core of age and systolic blood pressure. You can see you get the same answer. And then I can compute my t-value. Does anything So I compute the t-value, which is r divided by the square root of 1 minus r squared over n minus 2. And I'll do this in a few minutes, but you see it's 4.004. Does anyone recognize that number, 4.004? Yeah, when I tested beta up here, when I had that table, that's this value right here. It's identical. In other words, testing beta equals 0 is identical to testing rho equals 0. So when I've tested beta equals 0, I have tested that rho equals 0. I don't have to do it. However, if I wanted to test the correlation of some other value other than 0, some rho naught, then it's a different story. If I want to test that rho equals rho naught, then what I do is what's called I transform R to a z-scale. This is an approximate normality as the logs base e of the square root of 1 plus r over 1 minus r. And then the z sub r is approximately normal with mean z sub rho over 1 minus square root of n minus 3. I didn't give an example of this because it's rarely ever done. In other words, it would be like, suppose I want to test a correlation as 0.5. You can actually do it using this, and I think the book may give an example. So if you want to do it, you can, but I'm not going to put a lot of focus on that. Okay, now going back to our studio just to show you how this works out. I'm not going to go, I'll let you sort of work through, I'm going to let you work through this hand calculation. I'm just going to sort of go through and say, okay, here's the core. Okay. I actually don't have R computed. In order to compute R, I have to go back and compute lots of things by hand. So I'm not going to go through it, I don't think. I'll let you sort of work through it. If you've gone through this and you've actually calculated all those S sub x's and S sub xy's further up in your code, then you'll be able to compute the t-value. But I skipped over them since I had done them last time, and I didn't want to go through all that again. So at any rate, the take-home is that there is a relationship, between B and R, that is the regression coefficient, and R. But B, you can think of R as being an unscaled version, that is, removing the units of measurement of B to get R. And when we do it, it turns out with the particular method we used that the correlation is between a minus 1 and plus 1. And that's nice because we now know how to sort of interpret things. If you get a 0.2, what does that mean? Well, that means a weak positive relationship. 0.4, a little stronger. 0.6, starting to get reasonable here. 0.8, pretty strong relationship. In fact, in our case, it was over 0.8, right? So it was a strong correlation. So you get up to 0.9, you got a really strong relationship. Now, this is a linear relationship. You may have a 0.2 and still have a relationship. It just isn't linear, so you got to check that out. Again, if it's a minus 0.2, it's weak, negative. Minus 0.4, not quite as weak, but still fairly weak, and so on. So again, by having these limits of plus and minus 1, it removes the scale, and it sort of gives us a way of thinking about how strong the relationship is. We can test it at 0, but if you've got a big enough sample size, you're almost certainly going to reject the hypothesis. You're going to say, well, it's not 0. But on the other hand, you might be more interested in, the actual value, and do I have a really good estimate of that value? So, are there any questions on this? Now, I encourage you to sort of step through, just like I'm doing, step through all the R code. And let me just remind you that I have notes here, and those notes are extracted from the book, and I've added a lot of R code which is not in the book. But that is not a complete substitute for reading the book. Okay? So, in other words, I've sort of abstracted out sort of the key points, but that doesn't mean that you shouldn't read the full book. Yeah.
for exams, are we going to have access to R for doing the computations, or should we know how to do it by hand?
No, you're not going to have access to R. But there won't be a whole lot of hand. I'll talk about that more later. In other words, I wouldn't have you compute S sub xx or S sub xy, but I might say, if I gave you those, could you compute R? In other words, the computations you do by hand, you'll probably want to calculate. I know it's yeah, but the calculations will be not very difficult. But I also may give you some R code and say, what does this do? Or in some cases, I may say, what is the R code to do? So all those types, or I may give you some output and say, interpret it. So those are all possibilities. It's not going to be a lot of hand computation. I don't want you to spend half the exam just computing. So you're going to use R anyway. Okay, any questions on this? Okay, well, you should read through that, and I will be giving... How are you doing on the assignment, by the way? Chapter 8. Not getting a whole lot of response here. Are you able to run the R code? I got one thumbs up. Are you able to run the R code? I mean, basically, the idea is to take my template, right? And you insert the R code with explanations. Now, my notes have quite a few equations in it. Your notes don't need to have hardly any equations at all. You're just explaining the output, things like that. There may be occasions, there may be occasions you have to put in a simple equation, but for the most part, and if you can't figure out how to do it in LaTeX, then you can kind of mimic it using carets and so forth. That you can kind of mimic an algebraic equation in text. But at any rate, for the most part, you won't need equations in the homework. You'll just need text, and so it's pretty simple, to do that. But is everyone started? I think I said not this Wednesday, but the following Wednesday is when it's going to be due. So sort of a little over a week from now. However, I'm going to be sending out Chapter 9 this week. So in other words, I'm giving you a little bit more time this first go-around to get accustomed to R. But then I will be giving you Chapter 9 a little later in the week. And that due date may be only a week later after this first one, maybe a week and a couple days, but it will be a shorter time span. Yes.
Are we submitting that just by emailing it to you? Or?
Yes. You need to email me the .onw file, and I'll email you the way I want you. Basically, I want you. I also want you to copy John Chen, and I'll email the directions. There's also a certain way I want you to label it. In other words, I don't want, if everyone, what did I call it? ASSIN1.RMD, is that what I call it? If all of you send me that, they're all identical. To me, they look the same. I have to open it up to see who you are, and hopefully you remember to put your name on. Remember to put your name inside. I should actually put that as part of the template. Did I put it as part of the template? If I didn't, I should. Well, you need to make sure you're on the inside. But I also want the name of the file to indicate your name. But I also need to indicate the course and the assignment. So I want to figure out some convention for you to use, because otherwise I'm getting emails from you and from my other class, and if they all start saying assignment 1, it wastes my time trying to figure out who's assignment 1, which class, and so forth. Okay, now I'm going to go into chapter 10. And we're going to start talking about the one-way analysis of variance, and don't tell me I also did that with chapter 10. That's cool. Gotta remember not to do that. Now I have to make sure that I don't accidentally copy it out of your file so you can't download it. Okay, there it is. Now I'm going to set the working directory to be chapter 10, and the workspace I'm going to clear. Okay. So I'm going to go ahead and create the chapter 10 HTML file. So we're going to do one way analysis of variance in chapter 10. And in 10.1, we're going to look at the additive model and what it is. We had a linear model with regression, alpha plus beta x. But in this case, we're trying to predict a y, but we're trying to pick y from an x that identifies a group. In the previous example, in chapter 9, x was a continuous variable. In this case, in the example we looked at was age. So in this case, we're going to know, are there group differences? So we want to know, can we predict y depending upon which group we're in? So in this case, the x is a categorical variable, not a continuous variable. X takes on certain categories or groups. So in chapter 8, we looked at mu1 equals mu2, right? Now, that's a special case of this. In other words, if we want to predict y based on two groups, we actually use the function called t-dot test, right? You should be getting familiar with this if you're working the homework in chapter 8. But in fact, there's a more general way to do this using the LM function that we used in the last chapter. So in other words, now we're going to extend the case where we have more than two groups. So if you were trying to distinguish, is there a group difference in chapter 8? Suppose you have three groups. Now we want to know, is there a group effect? And if so, which groups are different? The fact, if I have three groups, I could have a group effect, but maybe it's group 1 is different from 2 and 3, but 2 and 3 aren't different. That's quite possible. And so our strategy will be to first of all determine in a global sense whether there's an overall group difference, and then we're going to do what are called multiple comparisons to find out, well, which groups are different from which other groups. They may not all be different, maybe only some of them. And this gets into some subtle issues that we'll be talking about. So if we have A groups, I'm interested in testing the hypothesis that the mu1, which is the mean of the first group, is equal to mu2, equal to mu3, equals, and so forth. So if I look so it's sort of this way. So here's one group, here's another group, and here's another. So if I have three groups, and so, maybe this is mu1, and then here maybe this is mu2, and then this is mu3. If the mu's are the same, then those three groups sort of coalesce into one. You don't distinguish them. Now I'm making an assumption here. Just like when we did regression, we had to assume the variance didn't depend on age. We're assuming that the variance of all of these groups, that is the spread, is the same. Let's see, is this erase? Yeah. So we're assuming that the variances are the same. In other words, the variance don't depend on a group. If the variances do depend on a group, then we violate one of the assumptions, just like with regression, if the variance depended upon x, that violated an assumption. here, if the variance depends on the group, which is our version of x here, then we violate the assumption. And in order to test hypotheses, we're also going to assume normality. So what we're interested in is there really a group difference? That's what we're interested in. So what we're gonna do is we're going back here a minute. We're going to look at the variation within each of those three groups and compare it to the variation among the groups. So the variation among the groups is sort of the types of differences from here to here, from here to here, and from here to here. So if we look at the variation among the groups, and we want to compare that to the variation within the groups. So if the variation among the groups is very small, that means maybe those groups don't quite overlay each other, but they may be closely, they maybe almost do. And so, you know, in that case, we would probably fail to reject the hypothesis if those lines almost overlap each other. So how do we operationalize this? Well, in a general sense, if I'm testing the hypothesis and use the same, the sample variability among the groups is how far the means differ from each other. Then the numerator, if the groups overlay each other, that numerator will be near zero. But if the groups are very different, then that numerator is going to be much greater. And the sample variability within groups is the estimate of the sigma squared within each group, and then somehow we pull it together. So what is our model? The model, so now we have y sub ij. Y has two subscripts. I indicates the group, and j indicates the individual within the group. So a 1,1 means the first individual in the first group. A 1,2 means the second individual in the first group. A y21 means the first individual in the second group. Y22 means the second individual in the second group. Y31 is the first individual in the third group, and so forth. So we need two subscripts, one to indicate the group, and that would be the first subscript, and the second subscript, and that we denote by I. The second subscript we denote by j, which indicates the individual within a group. Now, we don't have to have the same number of observations within each group. Now, a lot of times, initially, we may assume that j goes from 1 to n. There are n observations within each group. But in fact, we don't have to assume the n sub i's are all equal. So n1 is the number of observations in the first group, n2 is the number of observations in the second group, and so forth. Now, initially, we're assuming that all the n's are equal. That is, we have the same number of observations from each group. But we don't have to assume that. So what is our model? Well, you might say that if we look at a particular group, you might say that y sub ij is equal to mu sub I plus some error. Let's call it epsilon sub ij, or something like that. So you might say, well, that's our model from I equals 1 to a. So we're saying that each y varies about its mean. But we're going to do something a little bit different than that. What we're going to do is we're going to actually write the model a little bit differently, which is given by this. We're going to write the model as y sub ij is equal to mu plus alpha sub I plus epsilon sub ij. That's a j. Okay. And where we view mu as sort of the grand mean. It's the mean of the means. And the alpha sub I is the deviation from that grand mean. So that's there's a reason why we do this, but even though we wouldn't have to do this in what we call the one-way analysis of variance, when we get to the two-way analysis of variance, then this representation becomes essential. Even though we wouldn't really have to do it for this one-way analysis of variance. Now, I'm assuming, again, in this type of model, I'm assuming that mu is equal to the sum of the mu sub i's over A. It's the average value. And then the alpha sub I is equal to mu sub I minus mu. In other words, if I have, it tells the deviation from this sort of grand mean. Now, if all the means are the same, if all the mu sub i's are the same, then the alpha sub i's is 0. But it's also true from where we defined it that the sum, that's not very good, the sum of the alpha sub i's is equal to 0 the way we've defined it. Because of the way we defined it here, the sum of the alpha sub i's will equal to 0. So we're going to write our model as mu plus alpha sub I plus beta sub ij. Let's see, these are probably telling me he's loaded some packages for my next class. So at any rate, this is our model, mu plus alpha sub I plus epsilon ij, but we have a couple of conditions. The sum of the alpha sub I is equal to 0 in this model. So alpha sub I tells you the deviation from this grand mean of the ith group. And then we also have that the epsilons are distributed independently, identically normal, mean is 0 and variance sigma squared. So that's our model. So you might ask, well, how do we estimate the among group variability and the within group variability? What I set up here is that we want a test statistic that somehow depends on the among group variability compared to within group variability. And if the among group variability is small, then that ratio is small, and we would fail to reject the hypothesis. If the ratio is bigger or big, then we would reject. Let's look at the formulas. How would I measure? Now, y bar sub I estimates mu sub I. And y bar, which is what we'll call the grand mean, estimates mu. So if I want to know how the mu sub i's differ from each other, suppose I take the sum of squares of y bar sub I minus y bar squared. In other words, I compare each y bar I to the grand mean. Now, if all the y bar sub i's are near y bar, that sum of squares is going to be small. Does that make sense? So look at this piece right here, right there. Well, without the bottom, but so if I look at that, if I look at y bar sub I minus y bar squared, if the mu sub i's are about the same, then that means they're also about equal to mu. That means the y bar sub i's are about the same, and they're about equal to y bar. So those square deviations are going to be small. On the other hand, if the means differ a lot, then the y bar sub i's are going to differ a lot. The sample means are going to differ a lot. And so that sum of squares of y bar sub I minus y bar squared should be large. Now we're going to, that sum goes from I equals 1 to A, and it's sort of like a variance, right? It's sort of like a variance. When I did a variance, I had like the sum of the y sub I minus y bar squared over n minus 1. Well, here I'm summing over A things. The sum of the y bar sub I minus the grand mean y bar squared over A minus 1. And so that's what we're going to, that's sort of like a variance, as I said, and we have to normalize it by multiplying by n. And we call that SS sub A, meaning the sum of squares due to the A effect. In this case, I only have one factor, which I'll call factor A, that has a certain number of levels. And I'll get to that when I see an example. I'll explain that in more detail. But that divided by A minus 1 is what we call the among group variability. The within group of variability, it looks at the variation within each group. So if I look at the y sub ij minus the y bar, sub I. It's the variation of the observations in the ith group. And perhaps I can draw a picture of that. So let me try to draw this a little bit. So if I have a single group, and this is mu sub I, I'm going to get samples. And someplace I'm going to have this y bar sub I, which will be hopefully close to mu sub I. And I want to know these deviations. I want to know how far each of these deviations are from the y bar. And so if I'm squaring up the deviations, that is, if I'm looking at the y sub ij for the ith group minus y bar sub I squared, so I'm looking at the deviations from j equals 1 to n. That tells me how much variability I have for the ith group, but I do that for all groups and sum over. So it's 1. I've gone over.
Yeah, 523 starts.
What now?
It's at 523 starts in 2 minutes.
Yeah, okay. I will stop here then. Sorry about that. Someone needs to speak up. I guess that's why Steve thought he could call me. Should have been clear. Sorry about that. At any rate, I want you to read all of this material. We're gonna go through quite a bit of chapter 3. We won't finish it next time, but we'll go through quite a bit of it. Okay, sorry about that.
There's an error in the last part of this equation, better equation. In the chapter 10, it's the last part.
I'm gonna print you one of these flyers so you can see it. It has all the major.
Yeah, that.
This is one posted on the
major.
Yeah, I haven't quite. That's why I have to edit. When I was editing, I didn't quite. That's why I said there'll probably be another update.
Okay.
There will be another update. Yeah, it's on the right above the Bonferroni. Okay. Okay, thanks. Yeah, this particular chapter, I didn't have time to do everything.
Me too. Let me throw off the equilibrium today.
It happens.
This guy's just sitting there.
Hey, I have stuff I need you to sign. I did a blue sheet for that.
Oh. You took that?
I took that, yes.
With your other camera?
Yes.
Yeah, that's good.
Your dogs are gonna hate me by the time this is over. Just so you know.
Okay.
There is a blue form, a gold form, and I believe travel. Make sure you sign it before you go anywhere, okay? And have
Okay.
Zach send it up. That blue form is for the Wolfram.
Oh, yeah.
the
Oh, you did
mathematics.
that?
Yeah. I put it on lab fees. Is that
Did
okay?
we didn't have to get approval for Mathematica because...
Well, if we already bought it, it's too late, isn't it? Oops.
Well, the university has a license, so I don't see why we have to get
I don't
approved.
think we should. But
Yeah.
I put it on lab fees.
Yeah, that's fine. That's fine.
Oh, sorry.
Who are you taking these pictures for?
Company out of Charleston.
Your photography company or?
Yes,